I would like to thank the organizers of FISO symposium for inviting me to present. And in this diagram, a black hole is engulfing a nearby star and converting material and the gravitational energy into radiation energy to become ultra-luminous X-ray source, which is one of the brightest objects as well as it's one of the most mysterious objects in the space. In this spectacular radiation dynamics, two forces dominate. One, gravitational force that pulls in materials, and two, the photon pressure force that pushes out the material. Therefore, in astronomical scale, photons, especially photon pressures, play a vital role. The topic of this talk is how such powerful photon pressure or force can be utilized for breaking the tyranny of the rocket equation. The fundamental question is, what is holding us from the space commercial revolution? The equation applies for conventional rocketry and shows the propellant mass exponentially increase as a function of the delta V, the spacecraft velocity. So that exponential increase is stumbling block of ordering the rocketry. In other words, the mission cost exponentially increases as a function of the delta V. This is one of the reasons that most of the commercial space activities are bound in the Earth orbit in the last 60 plus years. Very interestingly, recently, Mr. Elon Musk, in the interview by The Verge, stated that using those established means, it would be closer to $10 billion per person, which is completely out of reach for many people who might otherwise be willing to uproot their lives and make such a daring trip to Mars. If you think about that kind of a budgetary, they can be rapidly compared with the NASA FY 2016 budget, which is 18.6 billion. So that shows what kind of magnitude of financial pressure is even the travel to the Mars. I believe that we are at a similar junction as when the transistor was invented. Before the transistor invention, vacuum tubes were used for electronics, as we all remember. There was a time when vacuum tubes were used for constructing calculators, such as ENIAC shown here, and had calculating capabilities comparable with that of the modern-day handheld calculator. So that's pretty large size for simple calculating function. But that's the limit of the vacuum tube, and it was recognized by the developers at the time. Obviously, such a system could not be scaled to build modern-day electronics that produced computer information revolution that made the U.S. and the world economy flourish. That little device revolutionizes the whole world. That kind of invention is what we need in our space industry. In fact, the transistor revolution came with the invention of the integrated circuits, as shown in the middle. So imagine what kind of a magnitude of finance return that little transistor generated. That's what we need in the space industry. Analogously, the conventional thrusters cannot be indefinitely scaled up because of the tyranny of the rocket equation, and is predicted not to generate the spatial commercial revolution as we all wish. The conventional rocketry Dr. Goddard first demonstrated is shown on the black and white picture there. So one of the solutions that we are working on is the photon thruster. And I am predicting that a photon thruster, if we can be scaled up, will lead to the space commercial revolution. If we study rocketry, the first thing they teach you is ISP, which is specific impulse speed of the rocket plume exhaust. And that gives momentum so that the rocket can fly. So in this graph, the thrust efficiency, that is the ratio of the generated thrust to input energy as a function of the specific impulse, ISP, is plotted here. Please note that the plot is in log scale. So we are talking about orders of magnitude properties here. As the ISP increases, the thrust efficiency decreases. Low ISP thrusters, such as chemical thrusters, as shown in the left side, are more efficient than the high ISP thrusters shown to the mostly to the right side. Because of the special theory of relativity, the maximum ISP that can be achieved is 3 times 10 to the 7 meter per second, which can be achieved only by photon thrusters as marked by a red filled-in circle. That's the terminal point of our science in terms of rocketry. Because of the efficiency trend, also the photon thruster has the lowest efficiency among all thrusters. So photon thruster, is not bad. The reason it has such a low performance is because it has the highest ISP. So if you combine all together, it forms a one single rocketry equation system. You can develop the theory on that, and that fits with all the available data on various thrusters in a form of a universal specific thrust. So our terminal end is the photon thruster, but we are doomed because it doesn't have efficiency. So how can we overcome this? However, with the use of a beamed energy configuration in which laser source or photon source is separated from the spacecraft, the photons can be recycled between the source and the spacecraft, resulting in enhancement of the thrust efficiency. As the photons can be cycled more than 1,000 times, the photon thruster efficiency approaches that of the conventional thrusters, as indicated by the blue arrow. Therefore, they become economically attractive. The development of such recycled photon thrusters is projected to be potentially a game changer. For example, to make a Mars travel commercially viable, Mars travel should not last more than a week. In this graph, the specific energy, the energy required to speed up 1 kilogram of a spacecraft, that means the unit mass of the spacecraft to a velocity in kilometer per second, is plotted here. Please note that plot is again log scale. The vertical bars show the required velocity to reach Mars in 1 month, 10 days, and 3 days. Two curves shown are the specific energies with ISP 500 seconds, which is a LOX system, a chemical rocket based on liquid oxygen and liquid hydrogen of chemical thrusters, and 3,000 per second of electric thrusters. The straight curve represents the specific energies for photon thrusters with the recycling factors 1, 1,000, and 10,000. If Mars is needed to be reached in less than 10 days, for example, the conventional thrusters become impractical and too costly, and thus recycled photon thrusters becomes the only option in this case. Let us consider the technical aspect of the photon recycling for propulsion. In this diagram, two spacecraft platforms are shown, one with a photon source and a large lens or mirror, the other with a mirror and a high-power laser beam generated by the source is injected between the two mirrors. So such a configuration is also used to increase the length of the laser and the sample interaction. If the laser beam is bounced between two mirrors many times, each time when photons are bounced, thrust is generated. Thus, the thrust is amplified in proportional to the number of bouncing in this configuration. Such attempts have failed for more than 50 years because of the properties of the optical resonance cavity. Theoretically and experimentally, such configuration have been attempted, but it has not been materialized. We overcome the problem of optical cavity by inserting the photon source inside the optical cavity. We obtained the NASA NIAC grant to demonstrate such a configuration, and we successfully demonstrated the first proof of concept and coined such configuration of a photonic laser thruster, which is shown the first demonstration in 2006. Here, a thruster of 35 micronewton was generated by recycling photons about 100 times between two mirrors. And in this demo, a rod-shaped head was used to generate photons, and the two highly refractive mirrors trapped the photons. In the recent developed scaled-up versions of a photonic laser thruster, we now use a state-of-the-art thin disk gain medium instead of a rod gain medium. The gain medium was pumped by a fiber coupled diode laser, and then the thin disk was mounted on a diamond wafer to permit high thermal management, thus scaling up by more than 2 orders of magnitude was feasible. Slightly bigger platform compared with the first demonstration. The thruster stand for the photonic laser thruster for this scaled up demonstration is shown here. This work was supported by NIAC, NASA. Briefly, the recycled photon beam was generated by the thin disk laser head and bounced on a 45-degree mirror, high reflectance mirror of the 99.9% or even greater. Bounced on an output coupler mirror, which terminates the total laser beam path, and recycled back to the thin disk laser head that has high reflectance mirror coated on the backside of the thin disk. The photon beam is bounced on the thin disk mirror, amplified and recycled back to the pressure sensor and output coupler mirror. In this demonstration, in fact, as soon as we announced that we could generate several hundred kilowatts CW laser power in this configuration, right away Department of Defense and NIST contacted us to test their device, which is the radiation pressure sensor here, which measures pressure of the photon beam as shown here. And we generated about 500 kilowatts, and that results in hundreds of milligrams of photon pressure. Here is the results of photonic laser thrust measurements in millinewton as a function of the power, external extractable power in kilowatts. That is approximately 50% of the input laser beam power. Open circles are the actual thrust data. The maximum thrust in this data was about 3.5 millinewton, and the recycling laser power in the cavity was about 500 kilowatts. The typical laser weapons nowadays are about 30 to 50 kilowatts. So we are talking about 10 times of the laser weapons CW. So that's part of the reason Department of Defense started to contact us. In this particular experiment, the maximum amplification factor was about 900. So we are approaching 3 orders of magnitude. This one, compared with the previous one, we increased output coupler mirror reflectance further so that it becomes 99.99%, although the manufacturer said greater than 99.97%. So this graph represents a thrust measurements with a mirror with the depth high reflectance mirror. We could obtain maximum amplification factor 1,460. So that's more than 1,000. So we are very happy about that. And the thrust in this configuration was 2.1 millinewton. So compared with the previous one, why we couldn't get the higher thrust is that the mirrors, because we are pumping so much high power per unit area, the mirrors were flexing. As you can see, compared with the previous data, the data here are more scattered because of that thermal effect. And this is amazing. So here, the power density was more than 1 megawatts per square centimeter CW over the diameter of about 0.6 centimeter. So that is never been done before. And then when we crank up the power a little more, we could observe the laser mirror broke down at about 1 megawatts per square centimeter. That's something that Dawn could achieve. We are already having some spin-off technologies. Not only we are developing thrust technology. We tested the thrust in a test stand, the state-of-the-art radiation pressure sensor, etc. So we have to be able to accelerate objects. So we decided to set up a linear air track where the spacecraft can be floated in the laboratory environment in air. Use a photonic laser thruster to propel one new CubeSat. Here the amplified laser power was about 450 kilowatts CW, and thruster was about 3 millinewton. So if you press the play button, and this is a real time, by the way, laser is on. We have over 450 kilowatts of CW power is generated. The sparkling in the path of the laser beam is the plasma generated by the laser power by evaporating dust particles there. So simply looking at that shows the power density of this system. This type of demonstration that we shown here could be potentially the first demonstration of the transistor as shown in the left color picture there. If this becomes like that, then I think we may have pathway to revolutionize commercial space endeavors. So we do some historical review because we can learn from history and predict what would be the future. What is the pathway of a PLT, photonic laser thruster, to commercial space revolution? Let us review the history of the transistor success here first. Once the transistor was invented, it was possible to develop transistor devices stepwise systematically. So from the first transistor to the computers and iPhones, and eventually computer information revolution didn't happen overnight. Once the transistor was invented, it was possible to develop transistor devices. We can remember that in old days we have 1 transistor radio, 2 transistor radio, 5 transistor radios, etc. So that gave us the stepping stones to go further. Then the invention of the integrated circuit kicked in and enabled the construction of the early computers. Further development of the integrated circuits made network and application and all those commercial activities exploded, resulting in electronic or silicon revolution. And so we have a San Jose area dedicated as a Silicon Valley. One important aspect of the history is that each development step was profitable to generate return of investment as well as revenues for furthering R&D. Of course, judicial governmental stimulus and the venture capital investment play vital roles in the development. All these factors are crucial in developing photon thrusters, especially photonic laser thrusters, into a space commercialism success or revolution. So in sum, pathway to commercial space revolution require stepwise development supported by the return on investment. So without profit, we can go so far, and there would be not even IBM 360 or not even early stage Apple computer. Timely and judicious government stimulus such as the SEMATech are highly necessary. Another one required is a long-term, wise and enthusiastic private investment played highly crucial role. So do we have such, especially near-term potential for photonic laser thrusters? In fact, if we look into the capability of photonic laser thruster in terms of near-term applications, there are a wide range of exciting applications, and some of them are listed here. For example, ultra-precision in control of thrust magnitude and vector, and propellant-free, contamination-free operation, space operation. Inherent optical metrology for precision positioning can be done with the photonic laser thruster. Inherent power beaming to reduce swap of the mission spacecraft, and then providing the ultimate ISP. So there are a lot of goodies there, and then it's a matter of how to pick one of these and then start to work on it to generate some profit. And then PLT potentially enables, because of these capabilities, ultra-precision persistent formation plan that could not be done before with the conventional thrusters. Propellant-free or propellant-less station keeping and orbit maneuvering, and enhancement of the capability of small satellites such as CubeSat can be done. Application examples are virtual telescopes, synthetic aperture radars, and Earth magnetic field monitoring and distributed space systems or satellite systems. And all these were extensively talked by government agencies, including NASA, DARPA, and ESA. But they didn't really become very popular because tyranny of the rocket equation. So what would be the first transistor radio type of applications? So this picture shows an artist rendition of a small spacecraft such as CubeSats maneuvered with photon laser thruster. Here a large Shepard satellite equipped with a power source and a laser head and the controls, and it can deliver powers to the multiple CubeSats, and also it can control them as well. The multiple mission CubeSat can be used for wide range of missions. The ones involving large virtual apertures, clusters of CubeSats that a lot of researchers are talking about. And that would be similar to transistor radius as shown here. Yes.
Young, this is Harley. Got
yes.
a question that I should have asked this a few slides earlier, so this is a little bit of a go back. The amplification factor that you showed on, no heavens, what was it? The largest amplification factor that you've shown on your slides was, it's on page 15, an amplification factor of about 1,500.
Yes.
Presumably you are seeking modifications to the system, improvements and so on, to continue to increase the amplification factor. What are the changes, upgrades? Where are the major challenges in your system that you are working to beat?
Yeah. The mirrors that we use is the off-the-shelf mirror. So the high reflectance mirrors should be of high quality. And another one is the thin disc laser thermal management have to be improved. And we are using, for example, diamond wafer. And so those things can be optimized. So currently we are using the off-the-shelf items to just demonstrate it, but they are not optimized. So those are two factors that need to be improved.
Okay, so a follow-up. I'm sorry,
yeah.
Go ahead.
And then we are operating in air with some dust particles, so those need to be eliminated. So in principle, if we run this system in vacuum, it would be already like a 16 or 1700 amplification factor, because the dust scatters and absorbs the particles, the laser beam.
Got it. Follow-up question. So follow-up question to my follow-up question. So thank you. Is there in a previous slide you showed examples of performance if you could get an amplification factor of say 10,000. Presumably you or folks you work with have looked at what it would require in your system in the laboratory to achieve 10,000, for example. Are there theoretical limits, sort of fundamental physics limits, to what amplification you can achieve even in the laboratory, or could you go to, with sufficient engineering, hypothetically, go to 20,000 or 30,000? What, in your judgment, what is there a fundamental limit to the amplification factor?
Yes, there is a fundamental limit because of the material, the limitation of the material. So material cannot be improved indefinitely in terms of performance. And mirror flatness and mirror material, and then also the mirror has a thin coating, layers of thin coating on it, and that absorbs small amount of laser power, and they can be reduced down to like a ppm nowadays. And so all those things combined together, I would predict about 10,000 would be about the limit in terms of a technological limit. And scientifically, you can go much more, but technologically about 10,000. But practically about 2,000 to 3,000. So we are approaching there already. Yeah.
Okay. All right. Good. Great. Thank you.
Mm-hmm.
What about the beam divergence in the laser beam?
Yeah, that follows the typical diffraction limit. So if you go further up, you will need to have the larger mirror, and I'm going to talk about that mirror briefly a little bit later. Okay.
Okay. Thanks.
That's an excellent fundamental question, which is very, very important for scaling up of a photonic laser thruster. Thank you very much for raising that excellent question. We go back to the slide 21. This picture shows another example of a PLT for photonic laser thruster for perpetual station keeping of satellite in Earth orbit. In this configuration, PLT permits the separation of valuable mission platforms from the expendable resource platforms that carry propellants. This situation is analogous to the aerial refueling of fighter jets by tankers. In this way, the overall operation cost can be greatly reduced, but we haven't done exact logistics of a cost reduction yet. That should be performed later. Two mission scenarios are shown here. One is that a resource satellite in GTO, which is cheaper than GEO. So GTO station kits a mission satellite in GEO. Another is a large resource satellite in LEO. Station kits multiple small mission satellites in slightly different LEO. In such way, we can have orbit the orbit drag compensation here. We project that the overall operation cost will be reduced significantly with the use of photonic laser thrusters. And this is the concept proposed by some of the other colleagues I just briefly mentioned here. In this example, an X-ray interferometer of the length of about 100 meters to 1 kilometer can be formed with photonic laser thruster with or without tethers. Probably one can do it without tethers, and probably such a structure should be the Lagrange points. So that will be very interesting if we can do that in terms of a next generation X-ray interferometer that will cost much less than single structure space system. But this is sort of a scientific realm area. So I'm very confident that we can build a transistor radio type of applications. But if we want to go further up, then we have to visit scientific fictions. So it's a little bit highly imaginative. So now the question is whether PLT CONUPS can go beyond the Earth orbit applications. When scalable, PLT can revolutionize the space commercialism, as I asserted. For example, we can ask, can it be scaled up for two-way PLT structures, such we name it as photonic railway, almost like a railway formed with photon beams. They can permit one-way trip to Mars, for example, in 3 days. So here in this concept, a space train. So I call it, space train because it doesn't carry the whole propulsion structure, but it carries mostly crew cabin, food, and some entertainment devices. As a space train with a large mirror is accelerated at 1 G. 1 G is very desirable because it creates artificial gravity to the halfway point, then decelerate so that it can enter on Mars orbit. Such feats are currently considered to be definitely in the scientific fiction realm. So we are stretching our imagination. However, I'd like to remind you that smartphones and laptop computers, laptop computers are like old days of Cray computers now, or a scientific fiction realm when the transistors were invented. So I think if we can really delve into this development, maybe we will be able to achieve this maybe decades later. So back to the history. I predict that such ambitious space commercialism does not come cheap and easy. If we think, we can carry all the fear and go to Mars, that would be good for, 1 per decade type or 1 per 5-year type of exploration. However, it would not generate a commercialism. So if we look back, the computer communication revolution that we now witness required a massive infrastructure, such as infrared chip fab facilities. If you visit one of these, you just a mind-boggling, jaw-dropping experience. And we need to have a series of the concepts, cell towers worldwide, fiber optic networks, large-scale rare earth material mining. Without that, we cannot build the device, as well as crucial semiconductor R&D. Large infrastructures will be needed to move towards the space commercial revolution, even with the photonic laser thrusters. What do you can ask me, what would be your envision for such a large structures? In fact, NASA and wonderful other organizations are envisioned and worked on it, at least in terms of a concept level. So in this slide shows examples of such infrastructures for space commercial revolution with the photon thrusters. We need a power, so space solar power, back to space solar power, and which was thought to be sort of a debatable quality before, but I think it's a must if we go further up. And in space manufacturing, because instead of carrying everything around with you have to start to make devices in space, including in space 3D printing. In fact, NASA and also some other agencies are emphasizing that. I think it's very wise decision. And also, of course, before involving human travel, we need to have a robotic travel. So space robotics is highly crucial. And of course, autonomous space systems, to name a few. So what NASA and the other agencies are doing will be the backbone of the infrastructures for the future of photon thrusters for commercial specialism and commercialism. But for scaling up, I think we can go like tens of kilometers or up to 100 kilometers or up to 1,000 kilometers with the photonic laser thruster in terms of operation range with the current technology. And that's still we are talking about earthbound orbit. So how do we scale up? We will need IC type of invention, and that will be related. I'm predicting that will be related with how can we overcome the diffraction limit. The gentleman asked it before, and that's a very crucial question here. So one of the very crucial factors in scaling up photonic laser thruster or even photon thruster is overcoming diffraction limit. Currently, the science of photons is still in infancy, surprisingly, in terms of quantum mechanical nature of photons. So quantum electrodynamics is the one deals with the nature of photons, and the understanding is still very basic. I highly recommend the government agency to put resources on understanding quantum mechanical aspect of photons and then SNT to overcome the diffraction limit. In this decade, this has begun, in fact. Recently, German scientists discovered that photons can be frozen into rods that have diameters much smaller than the ones defined by diffraction limit, as shown here. The demonstration is shown here. That's published in Nature in 2010. And then it didn't attract too much attention, so I am very surprised about that. So the mechanism in this case is what they call Bose-Einstein condensation of photons as bosons. So this is the quantum statistical mechanics of photons. When the density is becoming high, then photons are entangled and they try to form a rod structure in a certain configuration, especially in the optical cavity configuration. When the photon density is low, as shown in the left picture, the photon beam followed diffraction limit. So the Bose-Einstein condensation did not apply. However, when the photon density is higher than the critical density derived from the Bose-Einstein condensation theory, as shown in the right picture, photons condense to form a rod that has much smaller diameter than the diameter defined by diffraction limit. So it's been demonstrated in a very tiny microscopic scale. Currently, such demonstration was feasible only in a very short optical cavity. And according to my theoretical investigation along with some other colleagues. I think we can extend length of the cavity here, but we need to have some simulation plus a lot of analytical calculations. So we need to have some support for that. Or some other theoretician, if they want to work on it, we will also welcome. We will need to investigate how to lengthen the cavity size to astronomical distances. So that's still questionable. But if we can froze the photons, that will be integrated circuit of the photon thrusters. So there's a little glimpse of light there. If the diffraction limits can be overcome, we will be able to build large-scale photonic railway, the multiple stations as shown here. So we can go farther and farther out. So this is still scientific experiment. I'm looking to much farther, almost as if iPhone when the transistor was invented. We may be able to use Pluto as a photonic railway station one day, and then that will lead us to the outside the planets outside of the solar system. So before ending the talk, I'd like to mention an intriguing fact on the disc-shaped space train. So space train is a disc-shaped. It's very strange, isn't it? If we zoom in the space train as shown here, it will be like the picture in the next slide, so number 28. The space train will have a crew cabin at the center and a highly reflective mirror or cell in the outer area. I warn you that this is a scientific fiction, so it's just for stretching the imagination of us. The space train will travel mostly at an acceleration rate of 1g or close to 1g. And the question is, what is happening in the crew cabin shown here? Question mark. We found in the cabin Star Trek staff. They walk casually as if they are on Earth because the artificial gravity generated by the constant 1g acceleration in casual uniform. So their imagination may be true, if this kind of system worked out one day. Although the picture is generated for fun, however, it has some point. The space commute for true space commercial revolution will be shaped very different from that provided by the conventional rocketry. In conclusion, photonic laser thruster or recycled photon thruster is projected to overcome the tyranny of the rocket equation if scalable. Photonic laser thruster has been successfully demonstrated in that. And PLT permits the near-term applications that can generate investment returns, which is very crucial for spatial commercialism. If we cannot, then that's the end of the PLT. Stepping stones for developing large-scale PLTs and the photon railways. PLT flight demonstrations in Earth orbit and mission studies and demonstrations are proposed to be the next logical step. So these are as I mentioned, the old transistor radios. The science and technologies, such as Bose-Einstein condensation of photons, which here are still in infancy, and overcome the diffraction limit of the laser beam propagation over long distance are recommended for the near-term R&D. Now, and this aspect is also very crucial for the space communication with the lasers. So if we can control this one, in fact, I did some rough calculations. There may be some glimpse over that. If we can reduce, for example, the target size of the laser beam by a factor of 10, you are talking about 100 times the reduction of the laser power, or even more. This aspect has to be investigated in terms of not only for photonic laser thruster, but also space communication with the lasers. Lastly, I would like to acknowledge the support from NIAC, NASA Innovative Advanced Concept, or NASA Institute of Advanced Concept, and also my colleagues and collaborators. Thank you very much for your attention.
Young, that was terrific. I enjoyed that. Particularly went from relatively simple laboratory concepts and nice drawing up into the far future. But you did that very neatly. We are coming up on the 1 hour after the beginning. Does anybody have any quick questions before we sign off?
Yeah, Harley. This is Lawrence Kuznets. I got a quick one.
Yes.
Have you attempted to contact Buzz Aldrin? Because Buzz Aldrin has an idea called a recycler for Mars that is very, very similar to your space train. And he doesn't have a mechanism for propelling it, but he has a lot of clout and a lot of visibility, and it just seems to me it would be a perfect marriage for you. He'd be extremely interested in this technology, and he's been trying to promote the cycler, the Mars cycler, probably 15 years. And I would urge you to make contact with Buzz Aldrin.
Oh, yes. I will do that. Thanks for recommendation.
Yeah, good suggestion. Yeah, very good suggestion.
Yes.
Other questions or comments?
Young, this is Dan Lester. I'm trying to understand what the practicable distances are between your resource platform and your mission platform. How far apart can they be and still work? And of course, it's going to depend somewhat on the size of the mirrors. But what kinds of distance scales are you thinking about for that?
Yeah. As I mentioned, for the near Earth activities, which is transistor radio type applications, we are talking about 1,000 kilometers.
Right.
Up to 1,000 kilometers. But then, of course, for shepherding satellite, those things will be within probably hundreds of meters, something like that. For precision formation flying, if we can do like a micrometer type precision formation flying, we are talking about hundreds of meters. So there's many applications. But with the current technology, with the size of a mirror on the order of, let's say, tens of centimeters, we're talking about up to 1,000 kilometers. But then if we can freeze the photons, then range will increase dramatically.
Right. Okay. But it's a long way to Mars, and so
long way to Mars would require a much larger platforms. So that's the reason I said you need to have infrastructures to build such mirrors. We're talking about hundreds of meter diameter mirrors, something like that.
Let me ask a related question to that. In order for this to work, your mirror optical quality has to be very high. And you're reflecting large amounts of power off of these mirrors, and some of that power is going to get absorbed. What kind of challenge do you anticipate in keeping your mirror quality excellent when you're shooting megawatts of power at these mirrors?
Yeah. In fact, surprisingly, if you make the mirror correctly, they only observe ppm. So surprising, because when you see that, the demonstration that I had, that's already close to megawatts, half megawatts. And the mirror heating is not that really big factor. In fact, although we don't have any cooling system or anything.
Right.
So if we can make a better quality mirror and better coating in terms of better coating, something like that, then this thing can be minimized, and also it can withstand a little bit of elevated temperature, like 100 degrees C, or maybe tens of degrees C. Then we can radiate it out easily. So that's not a major factor. But if we can, another aspect of Bose-Einstein condensation is if photons quantum mechanically condense, the imperfection of the mirrors can be smeared out.
Right.
So that works in both ways. So I think there is hope there.
Okay. Thank you very much.
Oh, you're welcome.
Right. Any last questions? Okay, great, everybody. Thank you, Young. Terrific presentation. And folks, please join us again next Wednesday afternoon for our next Future in Space Operations seminar. Take care, everybody. Talk to you then.